Any questions while I'm preparing? We wait a minute or two to be sure that we have everybody. Okay, what I want to do, we are almost ready. In principle, we are ready to do the standard model symmetry breaking. Remember what we did last time? Last time we studied the SU2. Let's write like this. To basically nothing, to no symmetry breaking through the vacuum expectation value of a Higgs doublet. The Higgs doublet situation means that when you write your SU2 transformation, which can always be written in terms of the Hermitian and traceless generators, this just ensures, this thing ensures that UU dagger is 1. This ensures that determinant of U is 1. And the doublet means, by definition, the TA are chosen to be the Pauli matrices. It could have been any generator, then we will get any representation as long as the algebra of the group, which we often call SU2 algebra, it's also SO3 algebra, is satisfied in terms of these 3 generators. There was a doublet. We found out that phi 0 had to satisfy. The phi 0 is the phi vacuum expectation value, or VAV. Had to live on the vacuum manifold. We set a wall phi 0 so that the potential is at the minimum. I wrote this potential many times. I don't have to do it now. And that was a fixed absolute value. And that some of you knew was a 3 sphere. And we showed explicitly an immediate consequence that the mass of the gauge bosons is 1 and the same. All 3 gauge bosons get the same mass. This is very interesting. By the way, I ask you to think if you could guess why. It's kind of interesting. Why, we could ask. After all, the symmetry is broken. What do I mean by the symmetry is broken? I mean that TA acting on phi 0 is of course non-zero. Since phi 0 is non-zero, TA is non-zero, Pauli matrix is choice. Clearly, well, any choice of these matrices, any linear combination, any unitary combination would satisfy this. So all generators are broken, we say. means that U at phi 0, the vacuum is not invariant. This is equivalent. Means that vacuum carries charges. All three charges carries the value of these charges. We could say that there is a non-zero value of these charges. All of the symmetry is broken, yet I may come to this again. And then I was asked the question, what does the symmetry breaking depend on? Oh, maybe just one last thing to summarize in this short telegraphic review, that I can always write phi as e to the I GA over V TA I've chosen before, 0V plus H. I have four fields. So phi is a complex doublet, has four real fields. There are many ways of writing a complex doublet. There are four real fields, H and GA. So this is my doublet. Then we said I can always choose phi unitary to be e to the minus I GA over V TA, this phi. And that's 0V plus H. We have only one physical field. That's the Higgs boson, which I will often just call Higgs, which is okay. We started initial situation with the doublet phi, four real components. I started with three gauge bosons, each of them two component. MA was 0 manifestly. The final situation after the symmetry breaking, I have only H, one real component, but I have AA, three component, all three of them. MA is non-zero, which means altogether here 4 plus 6 is 10, 3 times 2, and here 1 plus 9 is 10. It matches. Everything is okay. A fields, E tower, G fields. This was in the Higgs mechanism. We won't be studying that, but since there was a question, I said, I can always go from here in the Nambu-Goldstone limit when theta is constant. Here, theta A is theta A of x. When theta is constant, G equals 0 limit, gauge coupling, everything was in the covariant derivative. I can even write it here. The essence of what we do when we do the Higgs, we can stay here in the title page, is that there is, whatever the generators are, there is always a covariant derivative. Okay. G equals 0. In this case, what we found out, GA are physical Nambu-Goldstone fields. I cannot eliminate them. It's manifestly here. There is no gauge transformation, and MG is 0. obviously, since phi dagger phi is just V plus H squared. And the potential is always a function of phi dagger phi because of symmetry. This implies zero mass because they are in the derivatives. So no gauge fields, but we have three massless number Boston fields. They correspond to broken generators. There are three broken generators. Every time you break a symmetry, you get a massless. That's a Goldstone theorem, massless Goldstone boson. There was a side remark. We don't have to study this. This is not what happens in nature. As far as we know, maybe it does, but not yet established. So this was our Nambu-Boston limit to Levy. Now the question was, what does symmetry breaking, spontaneous symmetry breaking depend on? What does symmetry, spontaneous symmetry breaking depend on? You have your chance to ask questions if something was overlooked in my lecture last time. Well, first thing on the gauge group, group G. In general, some gauge group G breaks down to gauge group H at the end of the day through the vacuum expectation value of some Higgs field. This is generic. This is in general. What do I mean that depends on G? Well, for example, an example, we took one example was G was U1. Then obviously there is no choice. In this case, either you have no breaking, or if there is a breaking, you bring down to nothing because there is only one generator. U1 can be written as e to the I theta some generator Q. So in the case of U1, since we are studying spontaneous symmetry breaking, we have a unique situation. All of group will be broke because there is just one generator. Well, you can say, so no choice here, except that you may decide not to break the symmetry. But if the symmetry is broken, that means by definition, Q phi 0 is non-zero, and therefore no symmetry remains. Well, you can say that seems to be generic because I took G to be SU2, and I got that through the vacuum expectation value of the doublet. So here, I could have written that H is 1. Here also. So it seems that it does not depend on what I'm saying, that depends on the choice of the gauge group. You could say, look, whether I take U1 or SU2, here there are three generators, you broke three of them. So we can have a question. Always H will be equal to 1. Answer, no. So we need an example. H non-trivial. Can I provide such an example? That's what I want to do today. If I do it quickly enough, I will move to the standard model. I will finish the symmetry breaking study. I may come back to it, but the time calls for applying it to the world in which we live. So can you guess what examples? Have you any idea what would be different? So I said here, you see, I said it depends on the gauge group. That's for sure. I have to illustrate it, and then I want to show it. So here, what I want to argue depends on the choice of I. This is the example. Obviously, if I'm to change the symmetry breaking, I have to change the Higgs field with a doublet. So what should I take now? Let me take the same group. I want to show you that unlike the U1 case, of course, it will depend on the group, but also on the Higgs. So with doublet, I broke it. What should I take for the Higgs now? This is the Einstein, the New York Times Einstein cartoon doing physics, a beautiful thing. Well, I have to do it once when I'm not like this. Let me leave it. What Higgs should I choose? What would you choose? You want to try something else? Help me.
Triplet presentation.
Yeah.
This is how, you know, we do physics, trial and error. Let's try it with a triplet. So what is a triplet? Triplet means that TA, ij, is minus I epsilon aij. Well, let me remind you what it means. Triplet means that SU2 really is SO3. That's what I mean by triplet. These are the same algebras. So I can write some triplet. I can write in many ways. I can write it as a vector, but let me write it as a column. If you don't like it, you can always write. I don't like that. You can write. I can write some phi I times some, you know, unit vectors. That you can also do. I will be 1, 2, 3. We'll comment on that. There is also another way of writing, which is called the adjoint. But let's write it as a triplet, just to remind you of some group theory. So what does it mean that phi goes into O phi? It's a real representation. Phi i's are real. All these three i's, these are the O transpose is 1. And let's take the determinant of O to be 1. SO3. But I can always write O is e to the I theta TA. Now what I have to satisfy, obviously, notice TA is, of course, Hermitian and traceless, but O is real, therefore TA is imaginary. And that means that's anti-symmetric. There are 3 such matrices. T3 would look like this. This is what I wrote above. He has to be anti-symmetric and he has to be traceless. So obviously, this is the form. This is T3. This is what I wrote above this. It's easy to check to satisfy T3. So for example, T1 would be 0, 0, 0. You do the same thing. You put minus I here and here. It has to be anti-symmetric. It's very easy. And T2 is for you to write it up. How should I choose the potential? So this is kind of trivia. How do I choose the potential? It has to be symmetric. V is lambda over 4. Phi transpose phi minus V square. Almost the same as before. I take transpose because it's real. So this manifestly goes into phi transpose, O transpose, O phi, and that's invariant. Well, I wrote it as a doublet. Let me not do that. Above, I wrote it simply as a column. So I wrote like this, just to be sure that which goes into phi transpose, O transpose, O phi. And that's phi transpose phi. Cannot be simpler. Usual vector. In the vector notation, by the way, phi transpose phi can also be written obviously as phi times phi, as I wrote, or as you often write as phi squared. That's another way of choosing the invariant. So what is the vacuum manifold? It's set of all points phi 0, so that phi 0 transpose phi 0 is V squared, which is phi 0 1 square plus phi 0 2 square plus phi 0 3 square. There are three components, is V square. What is this manifold?
S2.
S2. Thank you. See, the vacuum manifold is different. The groups are actually different, SU2 and SU3. The algebras are the same, because SU2 by definition allows for doublet, which I have exploited up to now. And now I'm doing SO3, so the vacuum manifold is somewhat different. That's very important. And all I know now, I can take a generic value on this manifold, but what I'm gonna do here, I will use my freedom. Any point on this manifold is equally good. I can choose phi 0 to be like this. Let me put it Goran. That's my choice. You can choose it any which way you want. You can put V on the upper component, you can distribute it. You don't have to do it the way I did it, but obviously symmetry tells you in a doublet case, which you checked explicitly, that the result will be the same. So now in this case, I'm asking you to tell me what is H. Is there any symmetry remaining? Remember how I said G goes to H through phi 0. That was the definition of H. What is H? H was 1, nothing. There was no symmetry remaining with a doublet. What about now? Who's gonna whisk?
Is it SO2?
Yes. Thank you. That's what I like to hear. H is SO2. How do you see that? Well, there is nothing here. I can still rotate here. There is a freedom to rotate. Well, if I choose the vector along the z-axis, which I can always do, what remains is the symmetry along the z-axis. That means that I can write O still like this. Cosine theta, sine theta, 0, minus sine theta, cosine theta, 0, 0, 0, 1. Notice that O acting on phi 0 is equal phi 0 with my choice. Or if you wish, T3 acting on phi 0, this is equivalent, is 0. This generator is not broken. So I can rotate around the z-axis. Of course, T1 phi 0 is non-zero. T1 acted in the, here was T1, acted precisely on the third component. And similarly, T2. So you see, H, as I said, is SO2, but SO2 is also, you probably know this, is equal to U1. You have one generator which is not broken, that's U1. In other words, Q of U1 is equal to 2, 3. This is called U1. So sometimes you will see written in the books U1, someone likes to write, some only write SO2. They are, of course, the same and one the symmetry. Why? SO2 is this symmetry, phi 1, phi 2, going into cosine, sine, minus sine, cosine, phi 1, phi 2. This is called SO2. I will use this notation very often. So let's, all I can write phi 1 plus I phi 2 goes into e to the minus I theta. You can check, please, phi 1 plus I phi 2. They're equivalent. This is equivalent. So this is SO2, and this is U1. And this proves I don't have to do anything else, that symmetry breaking depends on the choice of the group, but also on the choice of the Higgs. There is no a priori result. It's in our hands. When we write down the new theory, it will depend on what Higgs we suggest. We will have a dilemma. Every time there is a new theory, we will have a dilemma. And the logical answer to our dilemma will be to use the minimal such field that agrees with nature. That we can call Weinberg's dilemma when he wrote his celebrated model of leptons in 1967. I will come back to that. At the moment, we are just illustrating. Now, this was a gauge theory. Remember, I'm studying gauge theories. I could have said that, but it was not necessary. I told you I'll be studying gauge theories. So really, the gauge theory theta A is theta A of x implies, I can write a Lagrangian for you if you wish. Lagrangian of this SO3 theory as 1/2 d mu phi transpose. D mu phi, well, you know how to write it. It's always one and the same. I don't worry about the fermions. I'm illustrating symmetry breaking minus 1/4 Of course, the Young-Mills field is the same because the algebra of SU3 and SO2 is the same. So this is really simple, the potential we gave before. And d mu, of course, why should I keep writing it, but just to cement it, it's always the same. The only thing that changes is TA. And TA are the generators that we've given above. They have to be Hermitian, they have to be imaginary, they have to be anti-symmetric, the form is unique. And they satisfy commutation relations. So you see, when I compute the gauge masses, so what I have to compute d mu acting on phi 0, which becomes minus IG. This is a constant, TA A mu A acting on phi 0. And this is manifestly minus IG T1 A mu 1 phi 0 plus T2 A mu 2 phi 0. T3 acting on phi 0 is 0. I hope I have said that. Let's check if I said it. Yes. This is very important. That generator is not broken. So I have an immediate prediction. Immediate prediction. MA3 is 0. It's simply not there in the derivative derivative. Well, I didn't break the generator. So the gauge boson won't pick up the mass. I continue. Minus IG. T1 had that factor of I. Where is T1? Here, as a factor of minus I. So this becomes A mu 1 what will I get here? Minus I. Let's write here. Will be minus I times V, 0, 0. Plus A mu 2. What is T2? By my choices. So this becomes, I wrote something which I don't like. Was it true what I wrote before?
It should be 0 minus IV 0.
I think, yeah, thank you. This was minus I. And here I think I'll get I. Or minus I. I think it's plus I because it's T2. So the element is 3, 1 is minus I. It should be correct. IV 0, 0. I think now it's better. So there is no I, it's G A mu2 minus A mu1, 0 times V. And what I get? 1/2 d mu phi 0 transpose d mu phi 0 is 1/2 G square V square A1 square. Let me write the mu index plus A2 square. What I got? MA1 is equal to MA2 is equal to GV. And remember, MA3 is 0. It's very different from the doublet case that we often call SU2. This is often called SO3 situation. The masses are not the same anymore. One is massless. That because there is an unbroken generator, there are two masses which are the same. Why are these masses the same? Usually when the masses are the same, there is a reason, right? There may not be, there are accidents, there are little miracles that happen. But it's sort of, we've learned in physics, or if you wish, why. What I mean by why is often the equality of parameters implies a symmetry or vice versa. Why do you think I got this result? What was H? What did I find H to be?
SO2.
Right, SO2. When was it where was it acting here? There was an SO2 symmetry here. So there is no difference between 1 and 2 gauge fields. Just like that there is no difference between the component of phi 1 and 2. That's what the symmetry implies. They must have the same mass. This is the product of the SO2 symmetry. I expected it. I didn't have to compute it. It's just the overall normalization. I mean, at the end, I know the mass will be proportional to V. That's the mass scale. And I know it will be proportional to G because that's how the guy interacts with the Higgs. So all I have to fix the coefficient, and that's why I did the calculation. Otherwise, if I just wanted to know the spectrum, it's silly of me to compute. So see, we have an interesting situation now what has happened. So I can always write, by the way, I can write phi is e to the I. Remember, it's not very intelligent. GI, TI over V, normalization. I can write like this, 0, 0, V plus H. You agree? The same trick that I always use. My Higgs field that shows the motion around the minimum moves around the minimum, and I use my phases. Now it seems that I have too many fields because I is 1, 2, 3. So you can tell me about what's going on. There is H, G1, G2, G3. So that means that I have 4 fields, but I started with 3 fields. But I had phi 1, phi 2, phi 3. What is going on? How can I get extra field if I write the usual way? Who can help me? I'm confused. What's going on?
I guess G3, T3, if we add G3, T3 on this 0, 0, P plus H, it will give me 0. I mean,
Precisely. T0 acting on V plus H, great, is 0. So there is no G3. I can write this, it's convenient so that I don't really what I wrote. In other words, phi is just, I cheated with notation just because it's convenient. This is what I should have written. So the physical fields, instead of phi 1, phi 2, and phi 3, I opted for H, G1, G2. Everything is okay. But I can go into the unitary gauge, which is e to the minus I, Gi, Ti. I write this convenient way times phi, and that's just 0, 0, V plus H. I have 2 less degrees of freedom apparently, but remember 2 massive gauge fields. Okay, so in other words, I got rid of G, I eliminated, V eliminated, G1, G2, but A1, A2 became massive. 2 degrees less in the scalar sector, 2 degrees more in the gauge field, so it all matches. The number of degrees of freedom is preserved as usual. How could this go wrong? I didn't even have to check that. Pardon. That, of course, is as we expected. So see what I'm trying to transmit to you, which is fundamental. The symmetry breaking, and you have to be very careful, will depend on the choice of the Higgs. There is a profound difference in these 2 cases. But notice what happened. I mean, everything I could have figured out. I knew that one generator was unbroken. They told me that there will be a massless gauge field. I couldn't get rid of that phase. I had the remaining symmetry I could figure out, which was rotation around the z-axis. I didn't have to do the calculation. I know when I take a vector in a certain direction, I can still rotate around the z-axis. In the doublet case, you see, there are only 2 components. When I fix it in one direction, there is nothing more I can rotate around. Okay, the situations are manifestly different, but I can guess in every case, if I think a little bit, I can have a good feeling of what is going on. And then what I said, this was very important, that I expected the 2 masses to be the same because there is a symmetry. There is an equivalence about the masses. But when I took the doublet situation, before, no symmetry remained. Let's go back. I keep asking you about this. Keep asking you, in this case with a doublet, we got no symmetry, but all the masses are the same. In this case, H is 1. There is no remaining SO2 or SO3 symmetries. Why in the world I got the same masses? Okay, this is a beautiful question. Let me give you a hint. I want you to think about it, but let me give you a hint. Every time I tell you a little more, and then you can try, sleep on it and try to tell me what happens. So I go back to the doublet case. So in other words, to finish the triplet case, G, which is SO3, breaks down to H, which is SO2, through the vacuum expectation value of the triplet. Doublet. G is SO2, but to me it's equivalent to SO3. I'm just looking at the algebra. Breaks down into H equal 1 through the vacuum expectation value of the doublet. But notice, phi, I can write, and some of you knew this when you told me the symmetry, someone, is a doublet complex field, which I can write as a set of 4 real fields. So what is phi dagger phi? It's obviously and the potential is a function by definition. I don't even have to write the precise form, which is a function of sigma I equal 1 to 4 Ri squared. What is really the symmetry of this potential? The symmetry of the theory was a gauge SO3, SU2 symmetry, of course. What I mean, remember, the Lagrangian was 1/2 d mu phi dagger, d mu phi minus v of phi minus 1/4 f mu nu a, f mu nu a. This Lagrangian has SU2 symmetry, of course, only. Because why? Because d mu has only 3 generators. So when you write your gauge series, you cannot be wrong. What you choose will be the symmetry of the theory, and you and I chose, or I chose, and you went along to be SU2. But potential itself, it's not in your hands. What is the symmetry of this potential, please? I need help here.
Is it global SU2?
Sorry?
Global SU2.
I don't know what you mean, global or local. Of course, in the potential, global and local is the same. But why do you say SU2? Look the way I wrote it. Where do you see SU? I wrote like this. Okay, let's go back. Let's go back on the SO3 example. Very important. The potential was phi transpose phi minus v square everything squared. This is equal to lambda over 4. If I write into the components, it will be sigma 1 to 3 phi I square, obviously, minus v square, everything square. You agree? Phi was phi 1, phi 2, phi 3. Notice it's a function of these three fields. This is manifestly S03 symmetry. Now look at what I'm writing here. So in the doublet case, this is a triplet. Phi is a doublet, but I wrote it. I don't know why notation confuses. Why don't I write it like this? I can also write like this. Will this help you? As if the notation is confusing you. So now the potential is lambda over 4, sum I equal 1 to 4, phi I square minus v square, everything square. What is the symmetry of this potential?
SO4.
SO4. It's somehow interesting that I needed to write. There is more symmetry in the potential. It's called accidental symmetry. You and I thought that the symmetry was SU2, but it's not SU2. SU2 is SO3. There is much more symmetry. No, I chose the web. Remember, phi 0 Goran was like this for a doublet, 0 V. I took V to be real. I had the symmetry to choose that. This is equivalent to choosing phi 1 0 plus I phi 2 0, phi 3 0 plus I phi 4 0. So this is equivalent phi 1 0 equal phi 2 0 equal phi 3 0 equal 0. No, phi 4 0. And phi 3 0 is V. The way I wrote. In other words, what is the symmetry which is remaining? What is H in the potential? No, I stop here. Please think over this. I'm asking, what is H? Tell me tomorrow. Stay tuned. We'll come back to this. I don't want to say more. We have to understand this. It's fun. We will learn a lot when we do this. I think this is a great time to have a break. If there is no question, is there a question? Okay, if there is no question, let's meet. I want you to sort of absorb this because I will redo the SO3 example in a more generic, more beautiful, more useful group theory manner that you can use for any group. So let's then meet. Let's take a little break. 7 minutes. It's 11:58. Let's meet at 12:05. You're allowed to answer my question even now, or what is H? If not, we'll do it tomorrow. Okay, questions, comments? Notice to summarize what happened. So just to make the summary. In the doublet case, doublet, triplet, what we found out tell me, what is the rank of SU2?
One.
And of course, it's the same algebra. The rank is 1. What is the rank of H here? It's 0. There is no symmetry. What is the rank of H here? SO2.
It's 1.
1. That was our T3, which remain unbroken, which belongs to Cartan anyway. So in other words, in this case, you see what happened? This is very important, okay? Here, maybe let's summarize this here. Rank broken, rank unbroken. So you may break a lot of symmetry, but the rank may remain the same. That's very interesting. There is a general situation. There is a kind of theorem. There is a, don't know if I want to call it a theorem, but maybe I could. There is a generic SUN for any SUN situation where rank of G is equal to rank of H. And it has to do with adjoint Higgs. It's called adjoint Higgs. And let me just illustrate it on SO2 and then we can generalize what we mean. So when I took SU2 to see what I mean, from SU2, I went to what is sort of SO3. I had a doublet here. And here I had a triplet. And in order to deal the triplet, I had to know the generators of SO3. And you imagine when I want to do analogous situation in SUN, it would drive me crazy. It would not be easy to figure that out. I could have done the following from a doublet. I could go to what is called adjoint Instead, I can do this, completely analogous, this case. And by this, I mean the following: doublet. So we have a situation. So what do we mean? Doublet transforms into U doublet, or we wrote it phi transforms into U phi. It's a matter of notation. This is my doublet. What is an adjoint? I'm going to use sigma. It's a matrix that transforms like this. This is called a joint representation. You will see in the moment why. This is not a matrix. This is a doublet. This is a 2 times 2 matrix. Notice the following, that if I choose then notice it is preserved. If I start with a Hermitian, it will remain Hermitian. Why? Because sigma dagger transforms in the same manner. Therefore, I will choose sigma equal to sigma dagger is what we call irreducible. You always form irreducible representation. Irreducible means the smallest possible that transforms the same way. You cannot reduce it anymore. Irreducible, obviously, is the smallest of a kind. Notice another thing, the trace sigma is invariant. Trace sigma, please look, transforms into trace U sigma U dagger, which is trace U dagger U sigma, which is trace sigma, invariant. So what should be irreducible representation? Well, trace sigma 0. To be irreducible must be the smallest one. So in other words, adjoint matrix sigma transforms as U sigma U dagger. Sigma is Hermitian and trace sigma is 0. By the way, I said I will do it for SU2. Notice that this is general now. I can immediately generalize to any SO. I didn't have really to say that I'm taking a doublet. I could have said that I'm taking a fundamental. I did it in SU2 and I will do it for SU2. But notice that this is true in general. In general, SUN, U is n times n matrix. And U dagger. And determinant U is 1, and U dagger is 1. I can actually do it immediately generally. Why do I have to tell you SU2? So if this is true, then I can write, I can expand sigma in the basis of traceless Hermitian generators. But I can as well choose the generators of the group. I can just expand like this because they spend the whole thing. If I wish. That's the most logical choice. I had to choose those generators, okay. So how big is A? How many such generators is SUN? I wonder whether you should know this. A goes from, in SUN,
n square minus 1.
right. N square minus 1 because they are traceless. If there were no traces, there would be n squared. But because of the traces, you cannot take. It'll be always one less, as we will see. See, I've just defined the general adjoint representation. This is how it transforms. This is true for any SUN. Notice how I formed the invariant. There are invariants that I can write. For example, typical invariant is trace sigma. This is invariant, but this is 0, so this is useless. So let's write some invariants. There is also trace sigma square, if you agree. This transforms as a trace u sigma u dagger, u sigma u dagger, which is trace u sigma square u dagger, which is manifestly trace of sigma square. It checks, and so on. So the powers of sigma, this is how we write invariants. So when we write the potential, there will be also trace sigma cube is invariant in the same manner. You can check if you don't believe me. Trace sigma to the fourth. I stop here because the potential has to be quartic. Well, we can write in general if we wanted any kind of invariant. Okay, these are invariants. So I'm going to write my potential as a function of invariant. And if I have spontaneous symmetry breaking, I will have some sigma 0 non-zero. This is spontaneous sigma break. But notice that sigma 0 transforms like this. Agree? Of course, sigma transforms like this. And sigma 0 is a number. We want to minimize the theory. We want to take all the derivatives. We take a constant. We minimize the potential. We'll minimize everything. This is a number. Therefore, it's a Hermitian matrix. What can I do when I transform unitary Hermitian matrix? I can make sigma 0 diagonal. Any Hermitian constant matrix can be diagonalized by unitary transformation. Since sigma dagger is sigma. So sigma 0 dagger is sigma 0. Therefore, it can be made diagonal. You know, like you choose the vector to be in one direction. Well, this funny matrix, I can choose I could call it sigma 0 Goran, but any fool would do that. It's not just me. It's trivial. That's the simplest choice. Now, if sigma 0 is diagonal, so in other words, sigma 0 is some diagonal matrix, which is V1 to whatever, Vn, it's n times n matrix, and it has to be traceless. So why don't I write explicitly? This tracelessness is not so important now here, but okay. If it is diagonal, that means that sigma 0 can be written as a combination of VA, V alpha, let's call it, times T alpha. Well, why V alpha? It may not be the same V. Let me just call it some coefficient C alpha times T alpha, where T alpha belongs to Cartan subalgebra. This is what diagonal means. This is, you remember what Cartan is? Cartan subalgebra is a set all the generators T alpha so that T alpha T beta is 0. Mutually commuting subalgebra. In other words, Cartan subalgebra is a subgroup of all the diagonal. Those that mutually commute, I'll make them diagonal. They are Hermitian. If they commute, I can make them simultaneously diagonal. This is Cartan in an SUN group. I can do that because T alpha is Hermitian. And they commute, therefore I can make them diagonal, all of them. But sigma 0 belongs to Cartan. It's diagonal, here it is. That's what I wrote about. One more statement and we are done. Remember when I said sigma transforms, on the other hand, as U sigma U dagger. I can always say that that transforms as e to the I, Ta, some complicated generator times sigma. This is any representation I can write in the following manner, where I don't know what Ta hat is. This is just a definition of Ta hat. But U sigma U dagger is 1 plus I theta A Ta, the fundamental generators, sigma, 1 minus I theta B Tb, the leading term. I'm just interested in the leading term, which is sigma plus I theta A Ta commutator sigma. Everybody sees that there is a minus sign here, plus. In other words, Ta acting on sigma is a commutator. That's what I mean by adjoint. This is the transformation property here. Let's say the transformation of sigma.
We have e to the I minus I in the
Sorry?
transformation. In the transformation, in the second line of the transformation. After sigma, we have e to the minus I theta.
Here?
Yes.
Why minus I?
So u dagger is u is e to the I theta a.
You mean here? I don't understand. Here or the second or third line?
Second line of the transformation.
But U dagger is in the third line. This is just the definition of theta hat. I'm confused when you say the second line. Is this the second line? Are you telling me here?
Yes, yes.
But that's the definition. Why should I choose the sign? I decide when I say that the doublet in SU2, I can say that the doublet goes as e to the I theta a sigma a over 2 times the doublet, or I can say that it goes e to the sum minus, call it alpha a sigma a over 2. The sign is up to me. Alpha a here would be minus theta a. The sign is arbitrary. There's no way you can define the sign of the transformation. Whether I call the angle theta or minus theta is the same, you agree? So in the second line, this is just the definition. I'm taking positive sign. Notice in the third line, I have plus I. So why would you make me? I took u to be e to the I theta. I took this one in the doublet case. In the SUN case also, I take e to the I. So notice my second line and third line are consistent with each other. I need your approval.
I think the her confusion was about TA hat and TA. I mean, she was referring like substituting u by e to the I theta a TA, and then there would be a e to the minus I theta a TA. I
But
guess.
it is, I don't understand. I have a problem. I'm saying, look, let me repeat again. U is always, I can always write like this for any representation. This is generic. TA, TB is I, some FABC, TC. Agree? This is just a definition. You must tell me whether you agree or not. I choose with plus sign. You can choose with minus sign. Actually, sometimes I take a minus sign. That's up to me. How I call my theta a. You agree?
Yes, but what is u dagger for the u that you wrote? E to the I theta a TA.
We'll come there. You agree with this? I have to go step by step.
Yes.
Thank you. Thank you, all of you, please. All right. So just to say, doublet, TA is sigma a over 2. Agree? Triplet,
Yes.
TA, IJ is minus I epsilon IJ, and so on and so forth. It's hard to remember that for SU2, it's very easy. This is in SU2. For SUN, it won't be so easy to generalize this for SUN. But anyway, so I said, so now this is generic. This was generic. Generic. So now So this was a little digression here for SU2. So now let's go back to our adjoint. Adjoint, I can say, transforms by definition as e to the I theta A TA hat. TA hat belongs to the adjoint. I can be even more specific, just to emphasize what I mean by that. Do you agree? This is just a definition. This defines theta A, which I don't want to know. It's a mess. There's some terrible matrices I don't even want to know. But I said that sigma, on the other hand, transforms as U, sigma U dagger, where U is e to the I TA theta A on the fundamental representation. For example, it would be, okay, TA on the fundamental representation, okay, which is n-dimensional. I'm doing SUN. Okay, in SU2, now I tell you in SU2, TA would be Pauli matrix. You understand what I mean by that? It's a 2 times 2 matrix sigma in SU2. So TA is a Pauli matrix. But TA, I don't know what it is. I have no idea. I go back, Jesus, how do I know what is this? Okay, it acts on some 2 times 2 matrix. So I go like this. I say sigma transform, and so I write U e to the I TA theta A sigma e to the minus I TA theta A. Is that okay? One is U, the other is U dagger.
Yes, that was my question.
But that's what I wrote.
Well, you can scroll up and it's e to the I theta A TA, the one that, yeah, yes, here, like you wrote the expanded form 1 plus I theta A, and then
Right.
epsilon 1 minus I theta A. So, I mean, now I understand what's going on.
I was right.
Yes.
No, I'm not guarantee. I'm not always right. I don't guarantee for everything that I say. Very often I'm wrong, but here I'm right. So I'll write it once again. This is 1 plus I theta A TA sigma 1 minus I. I can write TB theta A TA TB and so on. And this is sigma plus I theta A TA times sigma. I wrote once again, and so on. What I meant to say that if you know the fundamental representation, which in SU2 is Pauli matrix, you go back what I wrote, you know how it acts. Your complicated generator acts as a commutator. In other words, what I meant is in the adjoint, TA, I will never remember it by heart. All I know is that I can take this and I'm happy. This is for my fundamental. The building representation, right? In SU4, it will be some 4 times 4 matrix and so on. Fundamental, for example, equal to sigma A over 2 in SU2. So see what is beautiful in SU2, sigma is a 2 times 2 matrix. Once again, remember, sigma is phi A TA. And you told me that A is 1 to n squared minus 1. So in SU2, sigma is phi I TI. I is 1 to 3. There are 3 components. What is a representation that has 3 components? In SU2.
Adjoint.
No, this is the adjoint the way I said. I've just defined the adjoint, the S3 vector, but what is it, the representation that we talk about it for the whole day today? What's it called in SU2?
It's a triplet
It's
representation.
a triplet. This must be a triplet. Well, let's ask ourselves, is this a triplet? You see, for the triplet, you had to remember the form minus I epsilon I j k, but I don't want you to do that. I'm saying that, and you know, if I ask you what happens in SU3, for example, in SU2, it's a triplet. What would be in SU3? How many components?
It would be 8 component.
Right, sigma would be phi A, now I would write TA, and A would be 1 to 8. And how would this terrible matrix look like? It would look like this. You can check it. Sorry, not IJ, because IJ was 1, 3. Let's write better. BC, which goes 1 over 8. Where TA, you can now go to fundamental representation and find out where FABCD, but who will remember this? Where TA is lambda A over 2. They are called Gell-Mann matrices. I don't want to think about them. I don't want to remember what FABC does. I don't have to do it because remember the adjoint. So what adjoint does, you just remember the fundamental representation, sorry. So that you have to know. And then it follows. That's what I meant. So now we agree, right? Once again, sigma transforms as U, sigma U dagger, where this acts on fundamental. The beauty of the adjoint is that, and doing group theory is the following. You just have to learn the fundamental. Everything is built out of fundamental. I'll remind you as we go along. You don't have to remember other representations. For you and I, there is only a fundamental representation. Everything else we will build out of it. So in other words, sigma A over 2 in SU2, lambda A over 2 in SU3, and so on and so forth. But what I found out, bottom line, when there is spontaneous symmetry breaking, in the case of spontaneous symmetry breaking, I found out that sigma 0 belongs to Cartan. Remember, I could diagonalize it. I want to make my point here. Sigma 0 belongs to Cartan, which means that any generators of Cartan acting on sigma 0, remember it acts as a commutator, you agree? We just proved that above. Must be 0 because they are all diagonal. You belong to the Cartan when you commute with all the members of the Cartan. Alpha is 1 to R. R is the rank. The rank of the group is the number of guys in the Cartan. What is the rank of SUN?
It's n-1, I guess.
Yes. Remember, it will be n. There will be n diagonal matrices, but they are traceless. So, for example, in SU2, there is only T3, which is, you have to normalize it, but anyway, you don't really have to normalize it. It's just, there will be a half. When we normalize it, it's this. Just 1 you can write. In SU3, that's 2 minus 1. 1 is 2 minus 1. There will be 2. The second is identity, but it has to be traceless. There is T3. The rest is 0. There is T8. It's proportional. I don't even want to write the coefficient of proportionality, -2, and so on. 2 is 3 minus 1. Obviously, the tracelessness make it n-1. The rank of S1 is n-1. So what I have proven, however, we have proven that sigma 0, this was just a digression, preserves the rank. We found that the triplet in SO3, which is the same algebra as SU2, preserves the rank. This is because triplet is an adjoint, really. There is, in my notes on WDK, I show it explicitly. So please check it. And tomorrow I will ask you to be able to tell me how it works. I'll just summarize it. So adjoint representation. If you want to preserve the rank, preserves the rank. Always. Doesn't matter. In other words, with adjoint, you break G down to H so that the rank of G will be equal to rank of H, whatever you get. But you know, I said in SU2, sigma is phi A TA, which is phi A sigma A over 2. Sigma transforms is U sigma U dagger. What is it? That's 1 plus I sigma I over 2 theta I sigma phi A sigma A over 2 1 minus I sigma J over 2 theta J. This is the original. There is a piece which is phi A sigma A over 2 plus I theta I sigma A over 2 phi A plus other terms. Hope you're following me. I'm taking a few minutes more, but we are basically on time. And this I can write as phi A sigma A over 2 plus I theta I. What is this commutator? Epsilon, what is it? There is an I. Epsilon I A B, am I right? Sigma B over 2. Phi A. Correct? Are you checking on me?
Yes.
Thank you. So this is, let me write this. I'll take, oh, this is phi A. How should I write this in intelligent matter? I could write the following. Look what I can do. I can write this as phi B sigma B over 2 plus the same, this repeated. So I can take sigma B over 2 as common. Then I have phi B. I times I is a minus sign. Epsilon I A B theta I phi A plus. I think this is correct. This is by definition sigma B over 2 phi B prime. The transform. Right? This is sigma prime. This is equal to sigma prime. This is the transformed one. By definition, the transformed one I expand again. So this implies that phi b prime is phi b. Maybe I should interchange A and B to be more elegant. Why should I call it? So that means that phi A prime is phi A minus I. Let me interchange. So this should be I B A theta I phi B. I just interchange the name. No, there is no I. Please check me. I can be wrong. And bear with me just for a few more minutes. I sometimes finish ahead, but today I need a little more time. Epsilon I A B theta I phi B. This is the famous transformation of a vector. This is how the vector transforms. This is the vector, a triplet. I have just proven that triplet is an adjoint. It transformed with this epsilon symbol. That's a vector, as you know, because TF, the generators for T, this is equivalent to say that Tij is minus I epsilon Aij. This is the beauty. So I found that the vector preserved the rank. This is because a joint always preserves the rank. This is in SU2. If I did SU3 or SUN, I will find out that FA prime, here A is 1, 2, 3. FA prime would be FA minus not epsilon, there will be FIAB because the commutators would be different. This is the adjoint. A would be now 1 to 8. And you and I, we do not want to know this. We hate to know this. We don't want to learn things by heart. And we don't have to, because I can do that with the adjoint. This is why the advantage of the adjoint is. So the advantage of the adjoint is we often write the adjoint to be, we say that it is the product of n times n bar in SUN. Right? It transforms. Why? Because sigma transforms as U sigma U dagger. This is the fundamental, this is the anti-fundamental. So this is what we mean by, we often say that. And it preserves the rank. It is the, sigma is the n times n matrix. It preserves the rank. This is very important. Trace sigma is 0. Sigma dagger is sigma. So sigma has n square minus 1 elements, fields. That's all you have to remember. And my last comment, just to whet your imagination, please ask me here, okay? I'm trying to be as pedagogical as I can. I'm repeating myself just to make sure that this is all clear to you. Hoping that you will ask me if you're confused. And imagine that you believe, you're saying, I believe. Imagine that you are saying that the standard model, remember what the standard model is? This is the group of the standard model. It's kind of, strong, weak. They actually mix an electromagnetic, but doesn't matter. You can write like this. You are saying, I want to unify this. You have a dream, Einstein's dream. You say, I want to unify that. what is the minimal group that unifies SU3 cross SU2 cross U1? It's some G unification. Minimal. Who is brave to say what the minimal group is? This is not standard model.
The rank of standard model group is 2 plus 1 plus 1, so 4.
Very good.
So might be SU5.
SU5. You see, because SU5 is 5 times 5, so there is room for SU5. You see, there is a fundamental representation in SU5, which would have 5 elements. Here SU3x, and here SU2x. Obviously, you can embed the standard model in SU5. Well, obviously, it's very suggestive. This is called the grand unified theory. The minimal grand unified theory was built in 1974 in a beautiful expiring paper by George I. and Gleshow, the same Gleshow, the father of the standard model. They have sort of followed the original ideas of Patti and Salam. It's interesting that the same fathers of the standard model became the fathers of grand unification. So I'm just whetting your imagination. I'm not teaching you this. There is a beautiful possibility that the world is unified in SU5. SU5 must be broken to the standard model. But you just told me, aha, I know the rank of SU5 is 4. SU5 is not the symmetry of the world. It has to be broken. The symmetry of the world is the standard model. So that means that there is some field whose vacuum expectation value breaks the symmetry. Which field should I choose? Which field? I must preserve the rank. Which representation preserves the rank?
Adjoint.
Adjoint. You see what we know. You and I know that sigma is adjoint. From what I told you here, you and I can build an SU5 grand unified theory. We are now as good as George and Gleshow. If you get an idea after today's lecture, and maybe we should do that, before we split, at least, or come to the office hours and we do that. Oh, by the way, some people wanted to discuss. People had question, is today at 6 o'clock possible for you? I can be free at 6. I have some things in the afternoon. Okay, nobody's objecting. I will invite you for 6 o'clock if you wish to ask me questions. One day we'll do it at the end of the course, either this or in office hours for those that are interested. Okay, I'm sorry I took more time, but I wanted you sort of to appreciate the beauty of the adjoint, the power of the adjoint, and we will never anymore use the fields like triplets or such fields. Okay, in SU2, of course, it's trivial. I don't need to use the adjoint. But if you master the use of the adjoint, you can do that for any. It's called the adjoint because the field is adjoint to a generator. You see, for every generator, there is a field. This is why it's called adjoint. This is the meaning of the adjoint. The field is expanded in the adjoint. Okay, I stop here. I took like 10 more minutes. Think of questions before we split. Okay, if you don't have any questions, maybe I managed to transmit what I wanted to tell you today. There was a sort of lesson in symmetry breaking and a lesson in the a little bit in group theory. So let's go back tomorrow to the standard model. Let's build the standard model. Okay, tomorrow will be an important lecture. You and I can do it together now with what we know. Okay. Very good. I'll see you then tomorrow.
Thank you.
No.
You.
Thank you.
Bye now.